started? Are we ready? Now we're going to get in depth with chapter 11. Chapter 11. Wait, no, let me go with the topics. I want you to look at this again. Whoops. Make it so you can see it. You ready? Here are the 4 waiting line, and all of these are possibly on the quiz. Here are the 5 operating characteristics that belong to each of these 4, and you can be asked about any one of these. Like I told the other class, you need to put all 5 of these on a paper ready to go with the variable for each one. 2 of them have a P, probability, probability. 2 of them have an L, average number, average number. 2 of them have W, average time, average time. 2 L's, 2 W's, 2 P's. Have those variables ready to go, because a question may say, what would the average time waiting, or they say, what? Calculate W sub Q. You got to know what that means. W sub Q is the average time of customers waiting. So, anyway, so I have that for sure. These last 2 subjects are going to be next week or skip, one or the other. But at the PowerPoint in your chapter 11 text, this is at the very beginning. It's find the probabilities of arrivals only, not the full arrival service together. And this one's find the probability of service only, not arrival service together. These will not be on your quiz, and we're not covering them today. So it's either next week or skip, one or the other. All right, and just as a quick review, how would you recognize a question and say, oh, that's arbitrary, because you just saw what in the story? Good. And, oh, this one we just read is constant service, because you're realizing the description of the service is the same amount of time for each customer, and it might be a robot or a machine or something that's constantly given the same exact service. And then the other 2, it won't have a standard deviation, it won't be constant, you know it's exponential. You're trying to figure out if there's more than one channel or only one channel of service. And that's the other 2. If you see it's got 2 channels or 3 channels or 4, the 5 would be the highest I would go on a quiz, because the table only goes up to 5 channels on multi-channel. So 2, 3, 4, 5, or if it doesn't have that, just 1, you know it's the top one. And there's the page number with the formulas, but I'm going to show you how to use each one of the Excel spreadsheets, hoping that you decide to have the Excel spreadsheets. But what's most important is I'm going to show you how to, if you're using the Excel, what you need to write down on your quiz is work. To be fair to those who are hand calculated, it's going to be the similar amount of writing. So we're all in the same boat. Where are we going to start here today? I can't remember where I'm going to start. I'm going to start on, there's something important on slide 20. And this is, as a manager, and believe it or not, some of you are going to be stepping into management, however many years, 3, 4, 5, 6, 7, 8 years out of college. They're going to offer you a ton of money to be a manager, and you're going to be so excited, like getting a new car. And then you're managing people, and you realize, how stressful it is. If you find out that whatever you're managing is a waiting line system, if you happen to be at a business that's using a waiting line system, you're going to say, I need to reduce the probability of customers having to wait, or I need to reduce the average amount of time a customer is waiting. And in doing that, you have only these 2 options in most cases. Either you change the way it operates by new technology or how the system goes to decrease that waiting, or you open another channel. Those are basically your 2 choices. In the burger dome example, I'm trying to think, is this the one or not? Okay, they said we're going to try changing the system. This will be our first shot at trying to reduce that probability of a customer having to wait. They said while a customer's waiting, they're going to get a menu piece of paper and circle the items they want while they're waiting to get the cashier and hand it over. The order then starting to cook before they even got to the cashier, and this is an example of where you're changing the system to make it a better experience, so you can reduce the chance of losing money from waiting. Customer waiting, getting goodwill, having a bad taste in their mouth, but now they're so close, they're going to stay in line, go ahead and pay and eat, but they may not come back. I just was at a place where I watched a person leave. They were in line. And it just happened that person arrived with, there was like no line when I got there, and all of a sudden the line started forming, and this person arrived, and I watched them just stand there and go, oh, and they walked out and left, they go somewhere else. So it happens every day. I mean, it's not that uncommon. And that's your waiting cost. And that means there's something wrong with your system. There's something wrong with the waiting line system, whatever it is you're managing. So now, hypothetically, let me see. We're going to multi-channel, so we're going to 32. Before I get started on multi-channel, arbitrary, constant, this is one of the most important formulas from this chapter, which is the economic analysis. Being able to calculate that total cost. In real life, it's as hard as it could be to get this cost of waiting per interval of time, so many dollars per hour, so many dollars per minute, whatever it may be. Everything has to be in the same unit of time. But this is cost of waiting. You'll always be given to this for this class, so that means that you know there's an economic analysis question or two on your quiz, and you'll be given that cost of waiting. You'll be given that cost per channel. Now, if it's one of those three models that are all single channel, this right here is the number of channels you're going to put a 1. But if it's the multi-channel you're reading about, this could be a 2, a 3, a 4, or a 5. This is what you need to say, I got to make sure that this is for sure this model, constant, arbitrary, multi-channel, single channel, because that L would be different if you picked the wrong type of problem you're reading. This L is different for each one of us. But this L, average number in the system, is the only thing you've got to get to calculate to do economic analysis, which is one of those 6 characteristics, the one that starts with L. In fact, it's just L. The other L, the average number weighting, is L sub Q. And you can't get to L unless you calculate an L sub Q first. So when you're showing your work on an economic analysis, you're probably going to have to calculate this L. And if you use Excel, I'm going to demo this, but I want you to hear it first. You need to, if you use Excel, you're going to put L equals, used Excel, and then you put the equation in the cell that you're on, that you're pulling that number from, equals C6 plus C2 divided by C3, whatever it says. And then whatever cell locations are in that formula, you've got to identify each one of them. What is C6? Well, C6 equals, and whatever it is, and one word explanation, L sub Q. What is C2? C2 equals arrivals, and you get the number. That's the work you're going to show if you use Excel. If you did it by hand, then the work you're doing is going to be just as much as they're showing if they're doing using Excel. So in this first one, suppose management wants to evaluate the desirability of opening a second order processing cashier. This is another alternative to lowering that probability of waiting or lowering that average waiting time. Instead of changing the system, what if we just add a second cashier? Still a single line, but first come, first serve, meaning as soon as that person's at the front, they can pick either one of them, whichever one opens first. Let's assume a single waiting line is taking place, first customer in line, moving to the first available server. The operating characteristics for 2 servers. We're going to use the same as we used in single channel exponential as far as arrivals. Arrivals were 0.75 customers per minute. 0.75 customers per minute. My question for you is that a time or a rate? Rate. Because you see per unit of time. You're either going to see the words per unit of time, or it could say each unit of time, which is the same as per. But let's say you want to convert this to hours. Convert to per hour. Now, some people find that hard. So you get this printed and have it in front of you. Where's my conversion? Is this it? And you go, let's see, we're converting from one unit of rate to another rate. Converting time to rate, no. Converting per hour to per minute, but right here is per minute to per hour. 0.75 per minute converted to per hour would equal 0.75 times 60 minutes, the number in an hour, equals, so we're going to take 0.75 times 60 equals 45 per minute, or per hour is the rate converting from minute to hour. Let's go back to service now. Service, in the last problem, it was 1 customer per minute. So now service is 1 per minute. I want to convert that to per hour. Per hour, this is too easy. 1 times 60 is 60 customers per hour. So here's per hour, there's per hour, or we can use per minute, either one. Whichever one we use, though, here's the deal. I'm going to hypothetically, I don't think it's on here, I'm going to hypothetically come up with cost per channel. Cost per channel equals, making one up, $11 per hour. I emphasize that because if you decide to use minutes, I gotta make sure I say this right. Yeah, I think we'll test the theory before I say what a mistake. I don't think it does matter. Cost per channel per hour. Cost for waiting. Let's say it says equals $8 per hour. Okay, there we go. The question will say, hey, right now we have a single server in this fast food restaurant. They're coming up, they're getting served, but it's taking too long. We have too many people waiting. We're thinking about opening a second cashier. The arrivals are at 0.75 per minute, and the service for one cashier, which will be the same for the other cashier, is 1 per minute. But you decide you want to do it in hours, and it says, and the cost per channel for each channel, if we decide to add one, is $11 per hour, and the cost of waiting we've estimated to be $8 per hour. So we have all the information we need except for L. So I think we don't have. Because this is multi-channel, you're not going to calculate the P sub O, the first one, probability of no use of the system, because it would take the whole test time to calculate it. So what do? We use that table. Multi-channel is the only time you got to use this table, right here. And to use this table, you take the arrivals divided by service. Now, if you take 0.75 divided by 1, or you take 45 divided by 60, you're going to get the exact same ratio. I'm just going to use 45 divided by 60 equals 0.75. There it is. Now we're going to go to the table and look for 0.75. I don't have a straight edge here, but I see it right here. And then, is this going to be a 2-channel, 3-channel, 4-channel, 5-channel? That we're trying to calculate that total cost. Are we adding a second, a third, a fourth, a fifth? How many are we adding? What's the total channels of service? 2. Go to the column for 2. 0.75. The P sub O, which is the probability of no use in the system, and both cashiers can do whatever they want, help clean, 0.4545. So I'm going to go from the table, P sub O equals 0.4545. And the reason you need this is because to be able to do this problem and find that right there, you have to have P sub O on multi-channel. And so I set up that spreadsheet where you enter the number of channels, the arrival, the service, and you enter P sub O, and everything else is calculated where you go.
So it doesn't matter if we don't convert it to hours?
We'll see. I'm going to see if we get the exact same L, whether we use minutes or hours. We're going to do it twice. So I'm opening up the multi-channel. Right here. Hang on, don't look. Hang on. There. Hang on. One more. There. How many channels do we have? How many channels is this problem? 2 channels. Arrivals will do per minute. So what will be my per minute arrivals? 0.75. We'll do, I'm sorry, let's do hours because I looked this up per hour, didn't I? So what is it per hour again, 45?
Yeah.
45, and service per hour is 60? And our piece of O we just looked up for 2 channels is 0.4545. Okay, here we go. What am I putting right now for cost per channel on this one? How much? What's the cost per channel? I'm going to do economics now. How much? $11. Thank you. Times, how many channels? 2. This is going to be $22, right? Plus, what's my cost of waiting? $8, right there. Times what? No. He said 0.4545. That's our piece of O that we had to use to get to what we need. There it is. Everybody hear that? The L, average number in the system. The 0.87, I'm going to round, 0.873. Now, here's the work. If you used Excel, then you need to put on a quiz for this. You're going to put L from Excel. And I'm going to put my pointer on that, and I'm going to look at what the equation was. Right here. H8, here we go, equals H8 plus, what is it, H4 over H5? H4 over H5, parentheses. Now, H8 equals, what is H8? 0.12, it's equals L sub Q, which equals 0.1227, is that what that is?
Yeah.
0.1227. Now H4 equals, that's arrivals I think, right? Arrivals, which equals 45. H5 equals, and then that happens to be service, which equals 60. There's the work. Every one of the equation you use, those have to be defined, and that's the work you're showing. All right, and if you want to use Excel, fine. If you calculate by hand, you're going to use that 0.4545. You're going to come up with the L sub Q, and then you know the arrival, and you're going to take that, add 45 divided by 60, which is going to be 0.75. I can almost tell you what this is because this is 0.75. So if this is, you just got to take 0.873 minus 0.75, you know exactly what that is, which happens to be 0.1227. Anyway. If you do it by hand, that's fine, because you're going to have just as much work as anybody using Excel is going to have to show. And now, what is the total cost? I should have calculated. What does $8 times this equal? About $7? Someone give me 8 times 0.8. 6.98. So this is 6.98. So our total cost comes to $28.98. Did anybody confirm 6.98 real quick? No confirmation whatsoever. We're on a total trust program here. Yeah. Okay. Is that what this is? All right. I hope it's right. Alexa, nowhere to be found. Damn her. All right. We're good here? We're good? Anybody? No one? Any questions? Did you do a multiple? Hang on, let me give this up here. Tell me what to do.
Wait, so you're going to give us the cost?
Always give you the cost for every one of these models. Cost of waiting, cost of that. Oh, we're going to do per minute now and see if anything changed. See if we have to change this to per minute and that per minute. You ready? Let's see if that happens. Still 2 channels. Arrival is 0.75. Is that correct? Per minute?
Yes.
Service is 1. 0.4545 still, we got off the chart. Is L the exact same number as it was last time? 0.873. So it doesn't matter. If we use per minute or per hour, you can use the cost of waiting and the cost per channel just the way it's given to you. And since this is per hour and that's per hour, then I'm going to put $28.98 per hour. If for any reason this is given to you per minute, you just do it like this, but then you would write per minute here instead of per hour. So there's our total cost. Let's compare it to 3 channels. Let's say, matter of fact, what is the probability with 2 channels? Did I change it? No. What's the probability with 2 channels that someone, a customer walking in is going to have to wait? What is it? Not all at once. No, almost though. Love it. There it is. Sure.
0.2045.
0.2045. There's a little 20.5% chance approximately that a customer coming in has to wait when we're using 2 channels. If we're using 3 channels, we have to change that piece of O. When I change this to 3, you're going to see a bunch of different numbers, but we also have to change the piece of O because it'll be a different piece of O for 3 channels. Matter of fact, before I change that to 3, let's go to our little table and tell me what is, now this is going to be 3 channels, piece of O equals what? You tell me, what was our ratio? We're looking at which column here, which number are we using here? 0.75. Now we're going over to which column? 3. And what is our 0.4706? 0.4706. So now we're going, where's the spreadsheet? We're switching this to remember we got 4706. 4706. Go up here, change it to 3. Nothing else changed. Our total cost with 3 is still, this is going to be 11 times 3, which is $33. We're already over the 28, so it's an overkill. Plus $8 times what? What is it? Point?
0.76.
We'll round it there. Okay, go one more. 0.765. 33 plus that is going to be, that's going to be, if this was 698, so that's going to be about 650. Where's my calculators? There isn't a single person helping. You're all busy taking notes or sleeping. Just stressed out about life. Is that what's happening?
In 6.12.
Thank you. 6.12. So we're at equal $39.12 per what? What's the money? Per hour? The $11 is per hour, the $8 is per hour, so that's $39.12. It's going to be less expensive to use 2 channels instead of 3. But my question for you is, what is our probability of a customer having to wait now that we have 3 cashiers instead of 2? 4%. They are. 4%. What was the last time? 20-something percent. 20-something percent or 20%. So we lowered it significantly. But look at the chance now of 3 cashiers being paid to do nothing. What's the probability of that happening? Let me say that again. The probability of no customers there and all 3 cashiers can play this new game they invented with all the time they have. 0147. There is, wait, that's not it. No, that's not it. What is it? It's there. I had to move my pointer. No, not 19%. No, say it. Say it again. 706. 4706. 47. This is the probability of no units in the system. A little over 47% chance, which really didn't go down that much because the other one was a little over 45%. But this went down significantly. Let's talk about this time. This stands for the average amount of time a customer has to wait. This stands for the average amount of time a customer's in the system. All right, so that WQ is the average amount of time a customer has to wait, which is 0.0196. Is that it? 0.02. How's that? 0.02 what? What is that? What is our unit of time on Natalie? I'm just so happy to see it. Remind me to give that back to you before you leave, okay?
Okay.
All right. 0.02 is what? How many units of time is that? What is the unit of time? What is arrival in? What is service in? What units of time? Is it hour? 0.75 and 1? Minutes. That is 0.02 minutes. W's, the 2 W's, are always the time unit of whatever you entered your arrivals and service in. This is per minute, that's per minute, you're looking at minutes. So 2/10 of a minute, I guess, 2/100ths of a minute, I guess. There's almost nobody waiting, and when they do wait, they're waiting so briefly because we have 3 cashiers working. I want to make sure you get this. I'm going to just change this a little bit here. Probability of someone coming in and having to wait, still very low. Nothing changed there. Right here, the probability of someone, of no customers there at all, the 3 cashiers could do whatever they want. That hasn't changed, this hasn't changed, that hasn't changed, 0.764, where is that? 0.765, excuse me. These have changed. These two are completely different numbers because we switched these two. 45 arrivals per hour, 60 arrivals per hour. That is 0.000327 hours. 0.00, is there a third one? 3 zeros, is there 3 zeros?
Yes.
0.0327, and this is hours. But it's supposed to be 0.02 minutes. Let's see if we're right. We're converting this hours to minute. Multiply that by 60 minutes. Tell me what you get. Where's our calculators? You never have calculators. Never. 0.1962 rounded is 0.02 minutes. This just happens to be in hours. Did you take notes on this? Because I feel like this could be in your future. All right?
Do it again.
That's not happening, but you can watch it on the video in slow motion. Slow it down. It's just too fast. Slow it down. Go.
Are these units in the same order that they are in here?
They happen to be exactly in the same order, except for this piece of O would be right here, but in multi-unit, we have to look it up instead of having it calculated. Only on multi-unit is why you're not seeing it there. Do you understand? Well, let's open up the single unit real quick. Whoops, that's not it. Which single? There. Notice it's there, right there. All 6 of them in the same order. And then we'll go now to constant. All 6 of them in the same order. But here's what I want to emphasize. On a quiz, they will not, probably won't be in this order. The whole point is as you being quizzed, I'm being able to recognize which one to use when they're not in the order. Putting together, I need L. What does L mean? O is the average number in the system. Finding which one represents L or the average number in the system. That's the whole point. That's figured out, showing me you know to use L in this formula and how to get to L. No matter which one of these 4 you're using. Good? Can we go another one here? We're going to slide, let's see. Let's go to slide 43. Wait, 43. Cutler University Student Union has 1 self-service copy machine. On average, 12 customers per hour arrive to make copies. Let me write that down. Where? Nothing to be no eraser. I already forgot. Is this time or rate on the arrivals? Time or rate? Rate. Because it says per what? Per hour. It'll say each hour, per hour, each minute, per minute. It's a rate. If it's not a rate, then it's time on arrival service. You must convert it to rate. You can't leave it at time. You need to see an example of that, don't we? Cutler University has a copy machine. They're arriving at 12 per hour is our arrival. Okay? Then it says the arrival follows place on distribution. The time to copy documents follows an approximate normal distribution with a mean time of 2.5 minutes. This is service. And then it has a standard deviation of 30 seconds. All right, here's a lesson to be learned. Right here. This pen's a little dead on me. Can everybody see this? Barely, right? I'm in trouble. Unless this one works. Standard deviation. This is 2.5 per minute. There we go. What kind of problem model is this one? What kind of service? What? Arbitrary. Everybody hear that? She said, we're getting it. We're going to pass on the credit. That's easy. Points maybe out. Extra credit. Arbitrary. But here's the deal. Arrivals are being given to you as a rate per hour, but service is given to you in time. And you need to convert it to a rate. It doesn't say 2.5 per hour. It doesn't say 2.5 per minute. It says 2.5 minutes. So we have to convert 2.5 minutes. And here's what I used to always do. I try to imagine I'm providing the service, and I help somebody for 2.5 minutes, and I'm trying to figure out an hour, and I said, okay, there's one person. 2.5 minutes go by, I'm at 5 minutes now, there's 2 people. 2.5 minutes go by, I'm at 7.5 minutes, I'm at 3 people. 2.5 minutes go by, I'm at 10 minutes? 10 minutes, I'm at 4, is that right?
Yeah.
But 10 minutes go into 60 minutes, 6 times, so 4 times 6 is? This is going to be 24 per hour. Or really all you had to do was take 2.5 divided by 60. Oh, I'm sorry, 60 divided by 2.5. Get a calculator, tell me if that's correct, I want to make sure. 60 divided by 2.5, anybody? Alex, you're all over it. 60 divided by 2.5. 24? 24? Alex, 24? Okay, there's how we convert it. And if we went to the conversion page, which I forgot to do, it would have been time to rate. Take 2 minutes, convert it to per hour. 60 divided by 2 minutes is 30. We have 2.5 minutes, so 60 divided by 2.5 is our conversion. I hope this helps. I'm going to repost it because I had that one, but I would have this printed right in front of you just because when you're in a hurry, the conversion, like I just did, we may have fallen apart a little. So now, we have arrivals per hour, we have service per hour, standard deviations always in time. You never convert the standard deviation to a rate, period. Let me repeat that, because it's the only one out of all 4 models, all variables that you leave in time and not a rate. Standard deviation is always stays as time, and you'll be given to you as time. It will never be given to you as a rate, and do not convert it as a rate. But, write a big but there. The unit of time has to be the same of whatever units of time you're using for your arrival and service. Everybody hear that? The standard deviation time units have to be the same of whatever units you're putting your arrivals and your service in. Now, what is our time interval for our rates for arrivals and service? Hours. 12 per hour, 24 per hour, 30 seconds. This will not calculate correctly unless you turn that 30 seconds to hours. I got that on here, don't I? Time to time? I think I do. Let's check. Converting time in seconds to time in minutes, and then take it to the next step. Oh, maybe I should have one. Converting minutes to then hours. To convert seconds to minutes, you just divide the seconds by 60 seconds. In this case, 30 seconds. 30 seconds divided by 60 seconds. 18? No, no. No, you must have went the other way. It's 30 divided by 60. 0.5 minutes. We just converted seconds to minutes by taking 30 seconds divided by the amount of seconds in 1 minute because we needed to convert the minute. And now we got to go to hour. 0.5 minutes. 0.5 minutes divided by 60 minutes in an hour equals 0.5 divided by 60. Jasmine or
0.0083.
repeat it. What's here? Hour. So we took 30 seconds, we divided by 60 seconds to get minutes. Then we took our minutes, divided by 60 minutes to get hours, and that's your standard deviation on this problem. But the person next to you may say, wait a minute, I want this to be in minutes, I want this to be in minutes, but then you would use the 0.5 minutes. You wouldn't have to convert to hours. You're converting these two to minutes, maybe. Okay? Now we're going to our arbitrary spreadsheet. Looks like this. Stop looking there. Hang on, there. How many arrivals? We're going to leave it. It's at per hour, and it happens to be 12. Our service, we converted 2.5 minutes to a rate, and it's 24 per hour. So those are both hours. Standard deviation has to be in the same time period, it says, which we converted to .008333. 3 is good, a couple more, why not? There we go, boom. All right, you just got told that our cost per channel, equals, what is this? Is this copy machine? We have to do the depreciation of the copy machine over the length of time it sits there, the electricity being used, blah, blah, blah. We're going to go with $8, no, it's lower than that. 5 is lower than that. $3 per hour. There's our cost per channel. Waiting cost. It's going to be really low. Students, if they get anxious, they'll go to, there's another copy machine in the next building over, and another one in the building after that. So this is really low. $1 per hour. $3 per hour, $1 per hour. We have all the numbers we need to do the economic analysis. And now the question right underneath it says, the first question says, what's the probability that in this waiting line, arbitrary, what's the probability a student walks up to that copy machine and has to wait? Tell me the answer. What's the probability? 0.5. And if you accidentally mix them up, they just happen to be both 0.5, just by coincidence. But this is the one I just asked. Arriving unit having to wait. There's a 50% chance, 0.5. Okay? You calculate it, or if you're using Excel, you would click on there. You'd say, used Excel. The equation is C1 divided by C2. Then you're going to say C1 is arrival equals 12. C2 is service, which equals 24. And there's your work, because you used Excel to get that answer. Then the second question says, if the cost per channel is $3 and the waiting cost is $1 per hour, you got to clear some space here, what would be your economic analysis? Oh, I shouldn't erase that, but you guys got it memorized by now. What is the economic analysis cost for this system, this copy machine? Well, what's our cost per channel again? $3? $3. How many copy machines are we talking about? One is a single channel. Plus, what's our cost of waiting? $1? And what number goes right there? Let me stare here. 0.76 is perfect. 0.76 is your L right there. And you got to tell me how you got that. Click on that cell location. You put the equation you see. Any cell location in that equation, you identify each of them real quick. And there's that. And then you do the calculation. 1 times 3 is $3 plus 1 times 76 cents is 76 cents, or turns into 76 cents. How's that? There you go. Equals $3.76 per what? Per what? Hour. Because that $3 and that $1 represented per hour. So this is your total cost per hour economic analysis right there. So it's not that expensive to have that copy machine there in the big picture. Except it's whatever. Okay. How are we doing? Yes.
How did you use the service rate again?
The service rate was 2.5 minutes, so I took 60 minutes divided by 2.5 minutes to turn it into how many per hour. 60 divided by 2.5 gives you 24. Or if you imagine, 2.5 minutes, I just served the customer. Now we're at 5 minutes, that's 2 customers. 7.5 minutes, that's 3. 10 minutes, that's 4. Well, there's 5 more 10 minutes, so 6 of them all together, 4 times 6, 24. So I always had to imagine it, because I always would forget this little equation. But this is on those help examples, there's one just like it on there.
Okay.
So it's just a matter of remembering you're taking 60 divided by whatever the amount of time is, if it's in minutes. That's the conversion on that one. So we just did arbitrary, right? If we did multi-channel, now we do it on time. Is this class done in 10 minutes?
Yep.
Just support. Oh, I don't like it. Good. I just realized I had a second, so I was going to say something. Okay, constant. Here we go. Going to go to slide 48. Got questions? Let's ask them. We're ahead of schedule by about 2 or 3 minutes here. You ready? Let me get rid of all of our work. This is brand new. This is we're at a Meijer or Kmart or supermarket or Walmart, wherever we're at, there's a pony up front, and you put 50 cents in, and everybody gets a ride for the exact amount of time that goes up there and puts 50 cents in, and that ride's 2 minutes. It's an electronic pony. It's always gonna be 2 minutes. You just go look, oh, electronic item providing a ride to kids for 2 minutes, it has to be constant. There's not a human involved. That's how you kind of know it's constant. Because if a real horse would give it a ride, it would never only be 2 minutes. Some will be 2 minutes, some will be just under, and a bunch will be over because they're crying. So in this case, 2 minutes for the ride, for the 50 cents, and their kids are arriving at 15 per hour. Arrive at 15 per hour, and the service equals 2 minutes. Andrew, I want you to convert, don't stop, I can hear you. I want you to convert this time to rate. And look at what the rate the arrival's in, so we want to use the same time period rate for the service.
30 per hour.
Because you took what?
I did 60 divided by 2. I was referring back to my physics, like canceling out units, but I figured it out.
There it is. We just turned the service to a rate. We have our arrivals at 15, service was 2 minutes. We recognized it was time and not a rate. It didn't say per a unit of time or each unit of time. Those are the key words almost in every problem to identify it's a rate. It will say per hour or whatever unit of time or each unit of time. Those are the key, and then you know it's a rate.
It's like 1 per 2 minutes.
It is, yeah.
So it is kind of a rate.
If you use 1 per 2 minutes, you just got to shrink this down to 2 minutes. This is for 60 seconds, 60 minutes, and then you could go down, divide by 30, you'd have how many per 2 minutes? If you have this 2 minutes and that 2 minutes, it will work out the exact same answer. As long as the unit of time for each of these are the same, you'll get the right answer. And it has to be a rate. How many, not how much. How many. We go ahead and plug this in. We're going, let's go to the Excel spreadsheet. Oh, real quick, this is a pony, right? The pony, again, like a copy machine, it has depreciation. We have this upfront capital expense. We depreciate over the multiple years we're going to use this pony. And then there's electricity to run it. And every kid kicks it when they're done, so we got to get repairs on there. So we're down to cost per channel of, it's kind of low still, because we got a lot of time out of this pony, like 15 years out of it. Wow. So we're looking at, I'm going to go with $4 per hour. That's high, by the way, but I had to leave room. Cost of waiting. We just heard a mother say she could never bring her kid back here again because the horse cheated, fell off the horse. So now we're in trouble. But it happens. So we're going to have a cost of waiting. It's going to be low though. Let's go with $1.50 per hour cost of waiting, because a kid couldn't wait 2 minutes for his or her ride, whatever the case may be, they're upset. I never want to come back here again. This is the only case that has a good voice. Okay, we'll go back. Here we go. $4, $50, $15, $30. I'm entering into the, I'm not even going to do it over here. Cost per channel, $4. Times, how many channels are we talking about here? 1. If it's not multi-channel exponential, you know it's 1, because all the other 3 are 1s. And then our cost per waiting, $1.50. $1.50 times, here we go. Instead of calling this constant, I call it pony. Hang on, take that out of it. And 15.30, right? 15 arrival, 15 service, 30. What do we put right there? I gotta look here. Tell me the number. 0.75, which happens to be L. I'm going to show my work. Listen, you want to see the work? Doing it by hand this time, maybe? Okay. I gotta remember the formula. The formula's right here. I'm looking at L and I realize it's using G13. So if I looked up the formula on the page that's given to you in that list of topics, the same exact formula, it's going to be L sub Q plus, so the formula here is going to be L sub Q plus arrivals over service equals L. So there's there. We got to go figure out how would it be hand calculated. We went ahead and looked at At paid, we see the formula that we got to take. Are you ready for this? 15 over 30, here's LQ. You got enough room here? I gotta go off camera? Darn. Here we go. Arrivals, 15 over 30 squared. There's our numerator. Our denominator, 2 times, is that 1 minus? 1 minus arrivals over service. Is that it? So, 1 minus 0.5 is 0.5. Times 2 is, not all ones. This is 1. This turns into a 1. And at 15 divided by 30 is 0.5. 0.5 squared is 0.25. 0.25 divided by 1, help me out. 0.25. So L sub Q equals 0.25. We plug 0.25 here. We add 0.5. We get 0.75. Derek, these rate notes so fast. This is for you. Here it is. L sub Q, 0.25 plus 15 over the arrivals over service, which is 0.5. We add them. We got our L of 0.75. Doing it by hand. And if you use this, you would write G13 plus G8 divided by G9. You would say G13 equals LQ, which is 0.25. G8 equals arrivals, which is 15. G9 equals service, which is 30. That's your work. That's how you got to this 0.75 here. What's our total cost? $4 plus, what is that? $1.50. 75% of $1.50 is $1. What is it? $1.12? $1.12? 1.125. So this is going to be 1.125 plus 4. Our total cost, economic analysis, total cost per 5.125 per $5, 12.5 cents per what? Hour. And the reason is our $4 is per hour, our $1.50 is per hour, so that total cost is per hour. Lex, is that a question? Just check. Okay. She was hammering her head with the pencil. I thought it was a question. It looked like it was going up. We got this one? This is it? So we did constant, we did arbitrary, we did multiple, right? These are easy now, right? I would highly consider thinking about using these spreadsheets. They're all there for you. That table. If you do it by hand, it doesn't take long, but this work is about this similar to the amount of work if someone's using Excel. You realize economic analysis could be for any one of these 4, right? It's the same way, just got to find that out. This question may be, there may be a second question on this that says, what's the average time a kid spends in the system? Now, make sure you realize in the system means the amount of time in the system is always larger than the amount of time waiting, because the amount of time in the system is including some of the waiting in a way. So, which variable or which number is the average amount of time in the system? What is it? Yeah, but what? No. What's the number I'm looking for? Average time in the system. Give me the number.
0.16.
No, almost. Almost. Jasmine, you have 50% chance. What's the other one? Helper. 0.05. But you are not going to put 0.05. You're going to put 0.05 what? What is it? Not per. It's just, what is it?
Hours.
Hours. But the question said, we misread it for a second, because it said, what's the average time a child spends in the system in minutes? This is telling you hours. You got to realize that. Because the arrivals in hours, the service is in hours. I'll go to our little cheat sheet here, changing time of one to time to another. This is in 0.05 hours, but we need it in minutes. Let's see. This is minute converted to hour. Here's hours converted to minutes. 20 hours, 20 per hour converts to, wait, this is a rate. We want time. Converting time to seconds to time in minutes. We want to convert time in hours to time in minutes. Help me out. What do we got here? This is in hours. We need it in minutes. 0.05 times 60 equals, how many?
3.
3 minutes. The average time a child spends in the system, waiting and writing, is about 3 minutes, 0.05 of an hour, times 60 minutes in an hour, gives you the amount of minutes that that 0.05 represented. That's it. That is the end of chapter 11, except Jasmine has one more question.
Okay, so WQ is the average time a customer has to wait. And W is just the average
Time in the system,
Okay.
which includes some waiting, so it's always larger. W is always larger than WQ. L is always larger than L sub Q. L sub Q is the average number of waiting, but L is the average number in the system, which includes some of the waiting, so it's always larger than L sub Q. Again, out of those 6, the 2 P's are probability, the 2 L's are average number, and the 2 W's are average time. Numbers, time, probabilities.
Can you go back to that for a second?
Which one?
The math part, yeah.
Which math part here?
On the Word document.
Okay, let's do it. Did I get one wrong?
Because shouldn't it, if you're going from hours to minutes?
I don't have that up here to show you. This is going from seconds to minutes. I should add, now I want to go from minutes to hours.
Can you not use the converting rate per hour to rate per minute?
Is it the same calculation? No. Wait, yeah, right here. Yes.
But wouldn't you divide if you're going?
But the only thing that's different here is that it's given us time and not a rate. It is the same calculation, though. It is the same calculation, but that's how much time a child spends in the system, and this is how many, but it's the same calculation, yes. It is, you just multiply times 60, because you're going from minute to hour, or no, hour to minute. So it is kind of different. This is going from minute to hour. We're trying to go from hour to minute, and we're multiplying times 60. It's more like this. This is going from seconds to minutes, so we're dividing. But we're trying to go backwards. Like if we were going from minutes to seconds, we'd be multiplying. I need to add another one right here, what we just had right here, which is converting from hours to minutes, right? There we go. And what was it, 0.05 hours? 0.05 hours, how many do I try? Hours converts to, parentheses, 0.05 times 60 equals 3 minutes. There's an example of converting from hours to minutes. Save. That'll be on the post tonight when I change this post. This quiz is your best one. This is it, unless you missed a lecture. Yeah. You witnessed him watching it? You were on the phone call? No. You guys are too young to care about the impeachment process. When you say exponential, are you talking about the factoring?
The exponential. Remember there's a single channel.
Yeah, that's the one we covered in last lecture. We covered the other three. Yes, I do. Yeah, right here. It's this one right here. This is single right here, single channel. Hey, I just remind you, this is single channel exponential service. It's also posted. I can't think of an example right now. The Burger Dome was 45 arriving and 60 service, I think, per hour or per minute. I think it was 45 and 60. If we only have one cashier at Burger Dome and there are customers arriving at 45 an hour, so one cashier can provide service for 60 an hour. There's our thing. What is the average number of customers waiting in this single service exponential problem? Burger Dome, cashier, 45 arriving. The cashier can provide 60 per hour service. What's the average number of customers waiting? I can't hear you. No, almost no. 2.25. This one, average number of customers waiting is L sub Q, 2.25 customers per what unit of time? Hour. Because 40's per 5 per hour, 60's per hour. This should say per unit of time. Because you could be using minutes here, and I don't want you to confuse it with hours.